Hey, I wanted to start the video by doing number 99 for you. So if you don't need it, you can fast forward through it a little bit. It tells us to use this position function for free-falling objects. And it says a projectile is shot upward from the surface of the earth with an initial velocity of 120 meters per second. So we got some information from that. Initial velocity would be our v naught t. All right, so we'll put the 4.9 t squared, and that initial velocity, it said, was 120 meters per second. Put that in for v naught. And we actually know the initial position. So if you read back over it, a projectile is shot upward from the surface of the earth. So it's like the coin. So here's the earth. It's shot from the surface. It's shot from the ground. So the position is 0, just like the position of the coin when it hit the ground was 0. So we've got that. What is the velocity after 5 seconds? Well, let me just take that plus 0 off. The velocity is the derivative of position. So the velocity is s prime of t. So we're just going to take the derivative. 2 times 4.9 is negative 9.8 t plus derivative of that's 120. So here's our velocity function. What's the velocity after 5 seconds? We're going to plug in a 5. Negative 9.8 times 5 plus 120. They didn't say what's the average velocity. If they had, we would have done that s of b minus s of a using the position function. They just said what's the velocity, so we had to take the derivative to get the velocity function. 4. Negative 49 plus 120, if I can multiply right, should be 71 meters per second. I'm not going to do the other part, but you would just plug in a 10. To get the second piece. Okay, so I would just say not everything. This is going now to new notes, 2.3 continued. Not everything that looks like a quotient is going to require the quotient rule. So example 6, A part, if you have y equals x squared plus 3x over 6, if there is a simpler, nicer way to do this than the quotient rule, I'm going to want to do it. And since it's just a constant on the bottom and not an x term and not a variable term, I'm going to think about this as being 1 over 6. So think about being able to take the constant out of the x squared plus 3x. Then it's much nicer to work. Your derivative would just be the constant times the derivative of x squared plus the derivative of 3x. And then if you want, you can put that back over the 6 to be done. B part is similar. Just because it is written as a quotient doesn't mean we're going to have to do quotient rule. However, on any of these, quotient rule works. You can totally do quotient rule. It's just it takes longer. So notice that that's just an 8 in the bottom, not a variable. So we have 5/8 that we could think about being a constant of our x to the 4th. So when we do our derivative, it's 4 times the 5/8, which is, you just write it, and then x to the 1 less. I'm going to reduce the 4 and the 8 by 4s. Take 4 out of everybody. And I'll get 5x to the 3rd over 2. C part. Y equals negative 3, parenthesis 3x minus 2x squared over 7x. So I would just say, what algebra can you do to rewrite it before you try to think about taking the derivative? So you might be tempted to say, well, let me pull the 3/7 out. But if you step back for a second, it'd be super nice if we just went ahead and distributed the top, and then we won't even need parentheses up there. So isn't that already nicer looking? And then what else could we do? Stuff that we did last time, like I love math, or everybody's got an X, let's take an X away from everybody. So you end up with -9 plus 6x over 7. Now you can think about that 7 as just being a constant in the bottom and see it as 1/7 -9 plus 6x. And that is going to be a really nice way to take a derivative. Yeah, that was a lot of algebra. That was a lot of simplifying that we did to get to this point. But the derivative is nice now. And if you think about doing low D high minus high D low on that thing, that wouldn't be too fun. So it's 1/7 times derivative of a constant is 0. And the derivative of 6x is 6. So make 6 a fraction and your answer is just 6 over 7. That's kind of funny. All that stuff had a derivative of 6 over 7. Okay, last one of these. What if you had 9 over 5x squared? Well, I do have an x in the bottom, but it's multiplied by the 5. So we could still say we have 9/5. But if I take 9/5 away, I'm leaving a 1 in the numerator. And now we want to move that x to the top to make it friendlier to work with. And now it's a problem that could have been on the other page. So it's just -2 times 9/5 x to the 1 last. And leave your -18/5 with your fraction and move the x to the bottom. All right. Let's get the derivatives of other trig functions. I'm going to go ahead and include sine and cosine. Excuse me, I had to sneeze. I'm going to go ahead and include sine and cosine. The derivative of sine, I have a reason, is cosine. The derivative of cosine of x is negative sine of x. These are ones we had the other day. Well, the derivative of tangent, turns out, is not cotangent. It is secant squared x. And the derivative of secant is secant x tangent x. So those are two brand new rules that don't have the nice kind of opposite value as sine and cosine do. But, whoops, can I move this? Because I have a reason. Can I do derivative of secant here? Secant x tangent x. So if you notice, I have derivative of sine on the left, and then I have cosine on the right. And then I have derivative of tangent, and I'm going to put cotangent on the right. Oh, I'm leaving off all of my dx's. You all are probably getting me. And then on the left, I have derivative of secant, and on the right, I'm going to have derivative of cosecant. So it's like I have all the co-functions on the left. Well, these aren't co-functions, but all the functions that begin with cos on the left. And just like we took the derivative of cosine and got negative sine, the derivative of tangent was secant squared. I'm going to... Did that work the way I wanted it to? Derivative of tangent, secant squared. The derivative of cotangent is negative cosecant squared. Derivative of secant x was secant x tangent x. The derivative of cosecant x is negative cosecant x cotangent x. So they don't work exactly like sine and cosine do, but every time you take a derivative of something that starts with the word co, or the beginning is co, you get negatives. So that's super nice. And if we could just remember these, then we would be able to get these. Derivative of tangent is secant squared. Derivative of cotangent is cosecant squared. So every time you take the derivative of the co, you get a co. Except for this one. I think I'm making a mess of this. There are relationships. Let's just say that. Okay, let's do an example. I'm sorry, I think I made a mess of that. Example 8. What if you have y equals x minus tangent x? Then the derivative of x is 1 minus derivative of tangent, we just learned, is secant squared x. B part. What if you add y equals x secant x? Well, I'm actually asking myself this. I just didn't say it out loud. And I'm saying, what type of problem is that altogether? Is it a sum and difference? Is it a product? Is it a quotient? And based on what it is, that's what rule I'm going to use. So since this is actually a product of two things, I'm going to have to use product rule. So first, derivative of second plus the second times the derivative of the first. And then you just clean it up a little bit. X secant x tangent x plus secant x times 1 is just secant x. Then they may factor a secant x out of both terms here. So this term would still have x tangent x. And this term would just have 1. Okay. If you don't care, look at example 9 on page 123 and just look at how they're able to do trig identities. 1 minus cosine x over sine. They did I Love Math on that, and they rewrote that to 1 over sine x minus cosine x over sine x. And they said, oh, 1 over sine x, that's cosecant x. And, oh, cosine over sine is cotangent x. So the first form, they did the derivative of this original thing, and they showed you how they worked it out with quotient rule and got an answer. The second form, they do the derivative of this, which is a sum or difference, and they show you how they get the answer. And they said, our answers look very, very different, but they're actually equal. So if we use trig identities, we could make those very different looking answers. If you look at example 9, we could use trig identities and show that they're the same. All right. Last thing I need to do with you is higher order derivatives. Do you know that if you start out with a function like this, x to the 5th plus 4x to the 4th plus 18x, you can take the first derivative. We have just called it a derivative, but it would actually be the first derivative because it's the first derivative we've taken. So it would be 5x to the 4th plus 16x to the 3rd plus 18. Well, we can come along and take the derivative again. In those double prime marks, that'd be our second derivative. We just take the derivative again. This time we get 20x to the 3rd and 48x squared and 0. Well, we can come through and take the derivative again. We can take the derivative as many times as we want. Fourth derivative, they quit prime marks and they start going Roman numerals. No, they don't. They write a 4. 20x plus 96. Fifth derivative, that's a 4, is 120. Sixth derivative, derivative of a constant is 0. Seventh derivative, derivative of a constant is 0. So every derivative past that would be a 0. But you can technically take the derivative as many times as you want. So that's the symbol if we're using f of x. If we're using y, we'd have y first derivative, second derivative. It's the same. Third derivative, fourth, use the 4. If we're talking dy dx, it gets a little crazy looking. First derivative. Second, they do d2y over dx2. And third and fifth, all the ones after that, it's d3y over dx3. And then there's more ways. I've not seen that fourth way that they've done on page 124, but I have occasionally seen the fifth way. Capital D, derivative of y, and this is with respect to x. So then the second derivative is the derivative of y with respect to x, and it's second derivative. So just some different symbols and notations we might use. But what's important to us right here is the position function is s of t. We can get velocity, v of t, by doing the derivative of s of t. Well, it turns out the acceleration function, a of t, is the first derivative of velocity, which would be the second derivative of position. So that's the relationship between them. And I would love it if you would ask me about example 10. If you could maybe put that in your notes and star it and try to remember to ask me about example 10. All right, good luck. Have a great break. Get lots of rest. Work on those Common Apps or college applications. All right, I'll see you all. Bye.